Hello, all. I think I can get started, AP. Um, Thank you for joining us. The Amber Book is presenting these series, and I'm very happy that you are joining me for a session on structures. My name is David Thaddeus, and I'm a professor at UNC Charlotte in North Carolina. We did a poll last week to see what are topics of interest. And it seems that shear and bending moment diagrams took 33% of the poll. So the topic today will be shear and bending moment diagrams. It is a pretty large topic, so I will have to go very quickly through it to accomplish what I would like to. And if not, then it will be continued at a future session. Very good. Can you see my screen? Somebody, Bethany. Everybody see my screen?
Yes, we can.
Very good. Thank you very much. I use color typically in lecturing, and I would like you to have the convention here. If I use red, I'm probably referring to compression. Blue is for tension. Those are axial forces and stresses. If the load is perpendicular to the axis, then I will use green for shear and purple for bending. And the resulting strain of bending stress is called deflection, and I will use brown for that. Okay, so this is an outline of the lecture today, and I forwarded these questions to you. I learned my lesson from last week. I forgot to address the question, so this time the question is right here, and the answers are here. But I don't want to go over the answers yet. I want to explain the topic first, and then it'll make a lot more sense. And you can download this presentation and look at the answers or listen to the Zoom recording in the future. So a free body diagram is a representation of all the forces, which is loads and reactions on a structural member. And I'm sure you're getting nightmares now from all the arrows and the free body diagrams and all the junk you hated at the time and that now you're totally detached from. Very good. I uploaded or I forwarded to the Amber Book 4 handouts. One of them is basically to calculate reactions, and I don't think I'm going to be able to get to that one today. I might just touch on it. This is the main handout. It's number 2 of 4, and it has several loading diagrams, and I would like to draw very quickly and explain the shear and bending moment diagram concepts. There will be a little bit of math, but it's very, very basic. You won't even need a calculator. Also, I uploaded a key to that page. That page has a key. I don't want you to look at the key. I won't look at the key. I'm looking at this one, but this one, after you struggle with it, would be good to go back and look at the concepts and the bullets in this handout. And then there is the last handout is shear and bending moment values for some typical loading situations. So on the ARE, they will give you a reference, or they might include something in the question. You just have to know what this means and how to use it. And I will explain in time what these cases are. For now, I would like to start by saying we have uniform loads. They are typically represented in your structures courses, in the steel manual, in whatever it is, with a coefficient and a resultant. I need you to understand that a deck and joists carry very light loads, and they are closely spaced and repetitive, and there's at least 3 of them. And so that is what a uniform load would look like. It is the outcome of a deck or joists. It could be in wood, it could be in steel, it could be in concrete. It doesn't matter. It's closely spaced and it's light loads versus concentrated loads. Uniform loads were per foot, and concentrated loads are not per foot. they are at one location over a very small area, and it's a much larger load. And the spacing is farther than joists. And usually you don't speak of a repetitive beam or a repetitive girder, but you do speak of a repetitive member such as a joist. So when it comes to a beam framing into a column, that is a large load and therefore a concentrated load. Be it in wood, steel, or concrete, a beam framing into a girder is basically a larger beam, is considered a concentrated load versus a deck. A deck is a uniform load, be it wood, steel, or concrete. It deploys a uniform load. So this one is pound per foot or kilopound per foot, but this one is a sudden burst of load at one location, and it is in pounds or kilopounds, not per foot. Very good. So the first thing in sizing a beam is to get the reactions. When we have a concentrated load or a uniform load, the load has to transfer to a member. And in this case, there is a left reaction and a right reaction. There is a load applied. It's like an action. And then there is a reaction to support that load. If that load is symmetrical, or if it's in the dead middle of a beam, then the reactions are equal. If, however, the load is closer to the left, if this is the center line, and the load is closer to the left, then the left reaction is larger than the right. If the load is over here, then the reaction is over here. This one is doing nothing because it's all on this left column. So, but the point I'm trying to make here is if the load is past the center line to the left reaction is larger than the right. If the load is closer to the right, then the right reaction is bigger than the left. We're not going to do math yet, but it's very important to understand this intuitively and qualitatively. So typically we have uniform and concentrated loads in the same loading situation. Here we can see a beam coming into a girder. That's a concentrated load versus a metal deck. I don't know how often it touches that beam, maybe every 4 inches, every 6 inches, whatever that pitch is of the deck, it is touching at these locations, and therefore that is considered a uniform load. Okay. You cannot put a heavy load, you cannot put a concentrated load on a joist or a deck. If you have a large load, a concentrated load, a chiller, or whatever it is, it's got to go on a beam or a big beam, a girder. So uniform loads are light and they are for deck and joist. They cannot handle bigger loads. So shear is basically where you have two opposite forces. Shear is about forces. It's not about moments. It's not about rotation. It's just about up, down, left, right. That's all that shear is involved in. Shear is high at the support. And shear is critical always at the support. So bolts, welds, connections, joist hangers, all of these guys are in shear. And if you get a failure here because of shear, it's catastrophic. The whole beam comes down. So shear failure is very dangerous. Bending failure, tension failure, compression failure are all dangerous, but shear is sudden. It causes collapse. The other are more gradual. So here's an example of shear failure. There is equal and they're not equal. In fact, the green one is larger than the resistance in red, so it pushed, it broke. If we look at this picture, on the left it looks like this precast concrete beam is bearing. They detailed it nicely, and it sits on that column. But over on the right-hand side, it looks like they forgot to detail it. So bring in somebody who's very, very strong in shear because the beam wants to go down, and the reaction is this angle here is transferring shear and preventing the beam from going down. So this pair of angles have to be extremely thick and sturdy. Steel is very strong in shear, but these are still 3/4 inch angles and pretty hefty. Anyway, so again, shear is critical at the support. What happens in the middle of this beam is bending and deflection. At the support, where down meets up, shear is critical and shear is maximum always at the support. So looking at this picture, it looks like there's a 4x4 temporarily supporting the roof. It looks like there's a couple of 4x4s down here, and there's this horizontal 2x10 that is subjected to a downward force and an upward reaction. And at the support, shear is critical. So this one is not going to bend and deflect. This one is more about shear. So if it were a smaller member, then it might fail in shear. I have an important note here that I added as I was looking at my slides. Short beams with large loads fail in shear. Longer beams will bend and deflect. Shorter beams with huge loads. I don't know what shorter is. It depends on situations. But if you have a 4-foot steel beam on a roof carrying a heavy chiller, that one is not going to bend and deflect. It's all about shear. But then the longer it is, bending and deflection kick in, and those are critical at midspan. So bending is when a load is also like shear, perpendicular to the axis of a member. It causes the top to go into compression and the bottom to go into tension. Together, red and blue makes purple, so we're going to use purple for bending. This is a simply supported beam versus a cantilever beam. In a cantilever beam, the top is in tension. In a simply supported beam, the bottom is in tension. And this is going to dictate the bending. There is a positive bending, there's a negative bending, and we need to know the difference between those before we get started with all these diagrams. So here's an example of a concentrated load. There's a hanger here hanging some pipes or something. There's another concentrated load. There is a beam of 4x4 or whatever it is spanning between these red arrows. And the top went into compression. The bottom went into tension. Together, compression and tension is called bending. Very good. Some materials are stronger in compression than they are in tension, and therefore the failure will happen on the tension side. Here's another example. Sorry, wood is very strong in compression. It is very good in tension, but it's better in compression. It doesn't help that there's a knot here that made everything go south. This is a picture we had last time, the stone lintel failure. Of course, stone is very good in compression, not very good. It can't span. So it failed on the tension side. In a cantilever, the top is stretching and the bottom is shrinking. Therefore, it reverses. The tension is on the top. This is called a negative. We will see this. This is called the negative moment versus a positive moment. There's this huge coring bit to core a tunnel in a mountain. It's huge. I cannot describe to you how big it is, but there's an 18-wheeler carrying logs. This thing is crazy big. And to get to the mountain, they have to go on the bridge, huge load. And you can start to see, you're not supposed to see bending and deflection. It's supposed to stay inside the member. In this case, you can see, look at the guardrail. Whoa. So there's some bending because a huge dynamic load is traveling on this bridge. Okay, so I would like to start with the conclusions before we hit the math and the diagrams and how to draw them, and we'll get lost in all the minutiae. I would like to spend a minute on why we're doing this. Shear diagram, maximum shear always happens at the support. And to design a beam, you need the maximum shear. It's going to tell you how much square inches of material you need. Wood, steel, concrete, doesn't matter. Maximum shear happens at the support. Maximum shear determines how many square inches of material needed. It doesn't say you need to have it vertical or horizontal. It doesn't matter. All it cares for is that many square inches. Versus the moment diagram. The bending moment diagram and the resulting deflection will happen between the supports. So shear is high at the support, bending moment is high between the supports. If the loading is symmetrical, it will be at midspan. If the loading is not symmetrical, it'll still be between the supports somewhere. We have to draw the diagram. But basically, your maximum moment is going to determine something called section modulus. All of you hate that. I know, I've been teaching long enough. Who knows what that is? It is the depth. So it says a 2x6 is better in taking load than a 6x2. That's what section modulus is. So the more depth you have, the better you will be in bending, in resisting bending moment. And then there is something called deflection diagrams that we don't study, but they too confirm the depth. Because whenever a beam bends a lot, the outcome is it deflects a lot. So there's something also you hate called the moment of inertia. It's unimportant. It's confirming the depth so that it doesn't bounce too much. I have this picture here from Arup and Associates, the foremost engineering firm in the world. It says, look at this crazy beam. It gets deeper in the middle. It gets deeper in the middle. That's the ideal shape of a beam. It's just not practical. And what it's saying is we need depth in the middle to resist bending and to minimize deflection. And also, all of this is doing nothing. In your beam, it's doing nothing. At the support, you need square inches, and steel is very strong and shear, therefore we can get by with very little material. But in the middle, we need depth. So that's the conclusion to what we're about to do. Okay, so shear diagrams. Shear diagram is a plot of the sum of forces to the left of any location on the span of a beam. We're going to take loads downward, negative. We're going to take reactions upward and positive, and we're going to travel along the length, the span of the member, and we're going to plot not the forces. We're not plotting 6 and 4 and 4 and 4 and 6. No, we're plotting the sum. As we travel along the beam, we're plotting the sum of forces from left to right, or right to left, doesn't matter, but the convention typically in architecture is left to right. Very good. So I want to go quickly through this section so that we draw together. I'm just showing you how it works. Basically, we are drawing the sum of forces. Over here, there's 6 skips, then nothing happening, and then we pass 4 kips, so we drop down. Wherever there's a concentrated load, there is a drop in the shear diagram. If there is a reaction, there is going upward. So that's what this diagram ends up looking like. It's a stepped pattern for concentrated loads versus a uniform load. A uniform load says there is a uniform load coefficient. And I trust that you remember all this stuff from your structures classes. If not, we're going to touch basically on it. But this one says you travel 1 foot and you lose a certain amount, in this case, 1 kip per foot. Travel another foot, you lose another kip, another foot, another kip. It could have been shallower the slope of the line is little w, that slope. So if it's 2 kip per foot, it's a pretty steep line versus a 1 kip per foot versus a shallower. So I'm not interested in the numbers right now. I'm just trying to say that the shear diagram will be a sloping straight line versus when there was no load between these concentrated loads, the shear diagram was stepped. Very good. So for this one, for a uniform load, we're going to start seeing a slope. And depending on the uniform load coefficient, the slope of the line is going to be dictated by that number. So here are the uniform load, and I'm doing the same thing. I'm taking this much, then I'm taking a little bit more, a little bit more, a little bit more, and I'm calculating the sum of forces and plotting it, and it turns out to be a sloping straight line. Okay, so let's look at some of the conclusions for shear diagrams. We're going to do this a lot more in depth. I'm just trying to do an overview. I'm much more interested in figuring out what this stuff is for than the actual mechanics, because on the ARE, it's much more conceptual than actual minutia. So if the loading diagram is symmetrical, then your shear diagram must be symmetrical. All shear diagrams will start at 0 and end at 0. Otherwise, something's wrong. Maximum shear occurs at the support. Please, this is extremely important. That's where the maximum shear is. That's where I need all the bolts. That's where I cannot cut a hole to let a pipe through or a duct. You cannot touch maximum shear. You try to, why? Because you're taking out area. Shear has to do with how many square inches. You cannot take out square inches to let a member through if the shear is high. If the shear is low, go for it. Vmax is equal to the reaction. This is extremely important. The maximum shear occurs at the support. The maximum shear is equal to the reaction, no matter what that reaction is. So if you need to calculate the maximum shear, just get the reaction. That's the maximum shear. A sudden drop in shear, like this one, is due to a concentrated load. So if I look at this partial shear diagram, the shear went from 5.2 kips, it dropped down to -2. Well, then that is the amount of the concentrated load, 5.2 plus 2. So a total drop of 7.2 kips. Versus, I look at this reaction here in red, it went from -6 and another 2. So this reaction is 8 kips. It's basically the total arrow. Okay. A sudden drop in shear is due to a concentrated load. A sudden rise in shear is due to a reaction. Shear diagram is flat when there is no loads, and it's sloping when there is a uniform. So if your reactions are unequal, you find the reactions. If your reactions are unequal, the maximum shear clearly is the larger of the two. In this case, it's 9 versus in the previous case, it's 6 kips. Okay, I'm sorry, you may not be following very well because you don't remember how to get reactions. Let's do a quick shortcut, very quick shortcut. I have a total span of 24 feet. I have a 9 kip load coming in at 8 feet, 16 feet, in a total of 24 feet. You remember from your silly structures courses, you sum moments about the left, then you multiply 9 by 8, and you do clockwise, counterclockwise. You go to the other side, you do the same, and then you check your reactions. We don't have time on the ARE for any of this. So we're going to do a quick shortcut, hopefully, that'll clear the air and get us going quicker. Okay. The 9 kip will break down in the proportion of 8 to the total. That's one reaction. And the other reaction is 16 to the total. So frankly, this is not rocket science. This is just sum of moments left, sum of moments right. I didn't write it out. I just wrote the conclusion. So it looks like 8 over 24 is 1/3. And 16 over 24 is 2/3. So my reactions are 3 and 6, but wait a minute, you passed the center line to the left. Well, then the left reaction is bigger than the right. Your two reactions are 6 and 3. Okay, I must be 6. You are 3. Let's try that again. Let's try it over here. I have 12 kips coming in at 6, 18 in a 24-foot span. So my reactions will be 12 kips times 6 over 24. That's one of the reactions. The other reaction is 12 kips times 18 over 24. So it looks like 1/4 of 12 and 3/4 of 12. Oh, but the load is closer to the right. Well, then the larger reaction is on the right. The smaller reaction is on the left. It's a lot quicker to get our reactions this way. I'm sorry, I didn't want to move forward with just these numbers. I wanted you to know where they came from. So let's learn this shortcut. It's very practical because if ARE is going to ask anything about math and reactions, this is a quick way of finding an answer. Okay, so conclusion, shear diagram. Maximum shear has less to do with span and much to do with loads. I didn't even give these dimensions because I don't need them for the shear diagram. I do need them for the moment diagram. So the sum of areas in the shear diagram of a simply supported beam must be equal to 0. So the sum of positive areas should equal to the sum of negative areas. Otherwise, something's wrong. The beam is not in equilibrium. So the sum of positive areas in the shear diagram of a simply supported beam should equal to the sum of the negative areas. Now, you have to be careful, leave enough area of section after notching a wood beam. If you have a wood beam and you took out some area, you need to make sure that the remaining area is good enough for maximum shear. Notching happens at the support. Shear is very high at the support. You took out area, you have to leave enough area. You cannot cut a hole near the support to let a pipe through because shear is very high here and you're subtracting area, not okay. Do it where shear is low in the middle. Okay. Punching a hole for plumbing, whatever. Vmax occurs at the support and determines the minimum area of cross-section needed for a beam. Maximum shear is going to dictate the area. It doesn't say anything about shape. Do what you want. Any of these are fine as long as they have the requisite square inches. Maximum shear determines area of cross-section. That's all that's important. See all these shapes? I don't care. Just how many square inches do you have? It's concrete. I don't care. How many square inches? It's a steel tube. Very good. How many square inches? It's a glulam beam. It's a regular 2x. It's laying flat. I don't care. It's just how many square inches. Maximum shear determines how many square inches of cross-section you need. Now, the next diagram is the bending moment diagram. We have the shear diagrams, and the bending moment diagram is a plot of the sum of moments this time. What is moment? Force times distance. To the left of any location, or else it's the sum of areas in the shear diagram. So here we're just going to find the areas in the shear diagram and start building the moment diagram. In the case of a uniform load, you're finding the area of a triangle or a trapezoid. The moment diagram for a uniform load is a curve, and the moment diagram for a stepped or concentrated loads is straight lines. I'm going to have a conclusion on this in a minute. So bending moment diagram is a plot of the sum of moments. We said that. If you have, what is this? If you have horizontal for steps, you have a sloped line for the moment diagram. But if it's a uniform load, your shear diagram is sloped, your moment diagram is curved. That's what this is saying down here. Now, for concentrated loads, there is a drop in the shear diagram. If you went from positive to negative, then your straight line was rising. Now your straight line is sloping downward. In the case of a uniform load, if your area was positive, your curvature is rising. If the area in the shear diagram is negative, then it drops. So for simply supported beams, again, the maximum shear is at the support. The moment is zero, and therefore the deflection is zero. But at midspan, the shear is zero. That's where we cut a hole, right here or here. That's where the shear is low, and it's okay to take out area. So at midspan, the shear is zero, but the moment is maximum, and the bending and the compression on the top and the tension on the bottom is maximum. And also the resulting deflection is very high. So the sum of areas in the shear diagram must be zero. The moment diagram is always positive for a simply supported beam, regardless of what kind of load it's carrying. Here is the tip that I think you need to take so seriously, and it answers all the questions that I asked. When asked about moment, ignore the question and think deflection, because whatever happens in bending moment shows up as a deflection. So deflection is the strain that results from the stress of bending. So I'm looking at this moment diagram here, and I'm seeing the deflected shape is a mirror of this diagram. I'm looking at this moment diagram. I'm looking at the deflected shape. If it were a cable, it would have deflected like that. Oh my God, my time is up. I haven't started yet. If you have a uniform and concentrated load, then your shear diagram is a combination of these two. Your moment diagram still will be a curve because you have a uniform load. Oh no. Okay.
There's no rush, David. We got a full group here. They're hanging on your every word. So
I'm panicked.
I wouldn't
I'm totally
too
panicked. Okay. It is important to understand the moment diagram, especially if it's concrete, because concrete doesn't do blue at all, no tension. So we need to know where the tension is to put the rebar. So I'm looking at this beam here that is typically concrete, is poured. A beam is poured on top of multiple columns. A slab is poured on top of multiple beams. So it's a continuous loading. And I don't know what the moment diagram looks like. I have no interest. I can tell you one thing: the maximum shear is going to happen at the support, and the maximum moment is going to happen somewhere in the middle. I can tell you as much. But I am much more interested in this problem of looking at the deflected shape, because it answers everything and their brother. The deflected shape looks like that. That's what a continuous beam would do. Okay, so there's tension on the bottom. There's tension on the bottom. Oops, the tension flipped to the top. Tension on the top, tension on the bottom, tension on the top, tension on the bottom. I need rebar on the bottom. I need rebar on the top. I need rebar on the bottom, rebar on the bottom, rebar on the bottom, rebar on the top. It is extremely important to understand this diagram. And it has nothing to do with the moment diagram. We understand deflection very well. We panic with a shear moment diagram and numbers, but we understand the deflected shape. So if you have positive bending, your tension is on the bottom. If you have negative bending, your tension is on the top. And I need to follow up with my rebar, wherever that blue dot is. And if you have positive joining negative, there's something called the point of inflection. And that is a very popular question on the ARE. The point of inflection is not positive and it's not negative. It's in between. It has no moment, zero moment. And that's where the rebar needs to be flipped from bottom to top. So if I'm looking at this diagram here, the deflected shape, I see the curvature changing right here. That's a point of inflection. That's another one. That's a point of inflection. That's a point of inflection. And I need to flip my rebar because it's the tension on the bottom, the tension on the top. So those are all points of inflection. And we just did what we need to know about concrete in this quick diagram. Okay. So there it is. I'm sorry. I forgot that I put this slide in here. So over here, over the column, the rebar is on the top. And between the columns, the rebar is on the bottom. And let's not complicate it. Maybe a future lecture will be about concrete. Very good. So again, in summary, shear diagram tells me about the area, how many square inches. Bending moment diagram and its corresponding deflection diagram that we don't draw is basically about the depth. It's not about the width. It's not about the area. It's about the depth, disguised as something called section modulus and something else called moment of inertia. Those are depth. One of them is depth square. One of them is depth cube. So these guys, you need to have depth if you want to reduce deflection. If you want to span, you need depth. Width doesn't help you because depth gives you section modulus against bending. Depth gives you moment of inertia, whatever that is, against deflection. Very good. So there's the full picture. Okay. I hope I can have a little bit more time. I want to do this one reaction question, and then I want to move into drawing shear moment diagrams and then answer the question I posed. Is there a quick way of getting the reactions? I'm sorry, we can't interact, but this answer is stupid. This one is typical NCARB. They say 10 goes here, 19 goes here. That's not true because they both share. Any answer, let me think for a minute. The center line is over here. It looks like the right of the center line has 19 kips and left of it has 10. Therefore, I'm concluding that the right side is bigger than the left. Any answer that says left is bigger should be out. And the sum of the reactions should be 29, correct? 10 plus 19. So if you have answers that don't add up to 29, they should be out. I think this is too much difference between the two answers. I'm left with 2. So can we get an answer quickly? I tell you what, I wish, now you're not going to like this, go back and listen to the recording. It'll make sense. I don't have time to some moments left, some moments right, exam over. So what we're going to do here is, I wish this were 10 kips. I'm going to balance that other 10 kips, but it's not 10, it's 19. I understand. There's another 9. I feel like expressing 19 as 10 plus 9. Hopefully none of you have an objection because this 10 kip goes here. This other 10 goes here. Very good. Now I'm left with only the 9. That's all I'm left with. And the 9 is coming in here, making the right bigger than the left. What are my intercepts? It looks like 8, 16, and a 24. And I am trying to balance the green 9 because I balanced the 2 blue 10s. I'm done with those. So now I am going to invoke that shortcut that we did a little while ago, 8 over 24 versus 16 over 24. So again, 1/3. I'm sorry, I keep the numbers simple so that we don't get confused. 3 and 6. So I have made an executive decision that the load is to the right of center. Therefore, the right reaction is bigger. I have 2 reactions, 3 and 6. You must be the bigger of the 2. And you are the smaller. So these were the reactions due to the green loads. So you're going to get another 6. You're going to get another 3. At the end of the day, it looks like the left is 13 kips and it looks like the right is 10 plus 6. So that is the correct answer. It didn't take long. We got to use these shortcuts. Don't panic with the numbers, and make sure you don't complicate life like your structures instructor taught you. Use shortcuts. Okay, enough with, I have to do this one. When you have a uniform load of 1,000 pound per foot or 1 kilopound per foot, that means every 1 foot, you're getting 1,000 pounds. So 24 feet later, you have 1 kip per foot and deployed over 24 feet. Then you're going to have a total of 24 kips, and your loading is symmetrical, so it's as if acting in the middle, 24 kips, which means my reactions are half and half because it is symmetrical. I just wanted to emphasize little w, kip per foot, versus the sum total. The resultant is 1 kip per foot deployed over 24 feet. Very good. We're going to do another session on reactions. Right now, that's not the focus I want. I want to get here, please. Hopefully, some of you have downloaded this sheet. I would like to go in there and remind you, if your total load is 12 kips and it's in the middle, it's 6 kips reaction on each side. As long as the loading is symmetrical, add up the loads and divide by 2. What I am doing in this exercise is keeping the 12 kips the same and keeping the 24-foot span the same, so that I can compare these cases and see which one deflects the most, which one has the most shear, etc. So that being said, each case has 12 kip total load and a span of 24 feet. Case number 2, we just did 12 kips times 8 over 24 and 12 kips times 16 over 24 and 1/3 and 2/3, 4 and 8. So those are my reactions due to this non-symmetrical case, 8 kips and 4 kips. So I don't need to draw any diagrams. If you're asking me how much is the maximum shear, I'll tell you it's equal to the reaction. 6 kips, that's the maximum shear. Don't draw diagrams, don't draw anything. If the reactions are unequal, it's the larger of the two. So it's 8 kips for case number 2. Otherwise, the maximum shear is equal to the reaction. If the loading is symmetrical, the reactions are half the load. That's it. There's no rocket science here. But we need to draw the shear diagram to get to the moment diagram. The shear diagram is the sum of forces going from left to right with reactions going up. Oops. Let's get a thinner pen. Reactions going up. There's no change in load here. There's no change in load. It continues. And then it hits at 12 kips. This used to be +6. And then it hit a 12. So it took it from +6 down to -6. Then there was nothing going on. And then another 6 kip reaction took me back to 0. Very good. Things are looking good. I'll do the next one. I'm plotting forces from left to right. I start with 8 kips. Go up 8 kips. That's the reaction. There's no load. You go horizontal. Then you drop down -12. You are at +8. You lose 12. You're down at -4. -4 kips. And then nothing happens. And then the reaction brings me back to 0. Every shear diagram must start at 0, must end at 0. Otherwise, something's wrong. The next diagram says go up 6 kips. No change. Then lose 6 kips. You're back at 0. Then there's nothing going on. Then lose another 6. You're at -6. And then travel across. And then there's a reaction, brings me back to 0. Very good. Things are looking good. The next diagram says go up 6. Then travel over. There's no change in load, so it stays constant. And then I lose 4 kips From +6, I lose 4, I'm at +2. Nothing going on, horizontal, no change in load, and another 4 kips, -2. Continue across, drop down another 4 kips down to -2, and -4 is -6, and then continue over and then rise. The last one says go up 6 kips, but this time there's something going on. Every foot, I'm losing some load. I need to figure out how much little w is. I'm losing 12 kips in a span of 24 feet. So my kip per foot is 0.5 kip to every foot. Every foot I travel, I lose 0.5 kips. 24 feet later, I will have lost 24 times 0.5, a total of 12 kips. So my shear diagram here looks like this. You go over 1 foot, you lose 0.5, 1 foot, 0.5, 1 foot, 0.5, 1 foot, 0.5. That's the little w. The loading looks like it's symmetrical. I'm going to cheat a little bit here and say at mid-span, you're going to end up at 0 because it is symmetrical, and therefore it'll probably do that, and the reaction takes me back up. So I need to ask you this question. How much is the maximum shear for cases 1 through 5, ignoring case number 2? It's the same. It's the reaction. It's 6 kips. That's how much the maximum shear is. It's equal to the reaction. If the 2 reactions are unequal, it's the larger of the 2. It's the 8 kips, not the 4. Now, to draw a moment diagram, oh my God, I'm so out of time. Okay.
This isn't even near the longest one we've had. So we haven't even hit 7 o'clock yet. And the group is very happy to be here.
Are they? Okay. So I hope we can continue. Okay. Let's do the following. The next thing we need to do is figure out, forget that. I need to recognize this point because the areas are going from plus to minus. I need to recognize this point, plus to minus, areas are changing. I need to recognize this point because areas are changing. Please, the moment diagram is the sum of areas in the shear diagram. That's why I'm starting to look at the shear diagram and examining it. I have 0 shear with areas going from plus to minus. I have 0 shear with areas going from plus to minus. So if your shear diagram is constant, your moment diagram will be sloped. If your shear diagram is sloping, then your moment diagram is 1 degree higher. This is all calculus. It'll be a curve. So I see a positive area, and it looks like the area in the shear diagram is equal to the moment. So what I have to do is basically calculate this area, and that'll be it, because I'll reach 0 shear. That will be the maximum. It looks like the height is 6 skips. It looks like the base is 12 feet. So area. Oh, I'm supposed to go to the next sheet. Where to cut? Okay, forget it. So here we are. I drew them better here. So I need to find this area here, because that area is the sum of areas to the left of 0 shear. It looks like the area is 6 skips times 12 feet, or 72 kip times foot. Those are units of moment, kip times foot. So it looks like the high point at 0 shear, the high point is 72 kip foot. And your shear diagram is stepped. Your moment diagram is going to be sloping straight line. If your area is positive, the straight line rises. If your area is negative, the straight line drops. Plus, the loading is symmetrical. the shear and moment diagram should be symmetrical. I have zero shear here. This must be the high point or the maximum moment. How much is it? It's the sum of areas to the left of zero shear. It looks like 8 kips times 8 feet. 64 kip times foot. Okay. Shear diagram is constant or flat line. Then the moment diagram slopes up. And then the area is negative, so it slopes back to 0. How much is that maximum moment? It's 64 kip times foot. So a little bit less than this. What this is telling me is if you put 12 kips in the middle of a 24-foot span, you're going to cause more moment than if you put the same 12 kips not in the middle. Okay. So this one says 6 times 8. 6 times 8 is 48 kip foot. Sorry, the math, we have some math, but it's not complicated. So we're going to rise to 48 kip foot. Then we're going to add nothing. So we're going to stay flat. Then we're going to lose 6 times 8. And my moment diagram is going to look something like this. For the next one, it looks like area 1. Area 1 is 6 times 6 feet. Area 2 is 2 kips times 6 feet. Or 36 kip foot for the first area and 12 kip foot for the second area, for a total of 48 kip foot. So shear is the sum of areas to the left. Bending moment is the sum of areas in the shear diagram to the left. So it looks like 36 here, and then 48. Rise to 36, continue to 48, come down to 36, come down to 0. So there's the moment diagram. And finally, this last one, the maximum moment occurs at 0 shear, and it's equal to this much area, the sum of areas to the left of 0 shear. So the area here is equal to base times height over 2, because it's a triangle. 12 over 2, area is 36. 6 times 6, 36. Kip times foot. So this one, the maximum is 36 kip foot. And if your shear diagram is sloping, your moment diagram is going to be curved. If your area is positive, the curve rises. If your area is negative, the curve drops. Plus, it should be symmetrical. So I don't like moment diagrams any more than you do. I just want to say the following. Can I do this quickly? Let me think. I'm sorry. Stop share. And let's share something else. Let's share this one. AP, can you see my camera?
Yes, I can.
Thank you. So if this were a cable and you loaded it in the middle, it would have done that deflected shape. That's the bending moment upside down for a single concentrated load. If you did 2 concentrated loads, it would have done that. That looks like the bending moment diagram for 2 concentrated loads. If you had 3, it would have done that. If you had a uniform load, it would have done that. That's the moment diagram for a uniform load and the deflected shape for a uniform load. So let me go back to where I came from. Stop share, and let's share that other one. This one. Sorry, I have 4 screens going on. I'm back here, and I would like to say this guy deflects like that. This guy deflects like that. This guy will deflect like that. So the deflected shape is a mirror pretty much of the moment diagram. Check it out. This one does that, and then a little bit, and then a little bit, and back. And the uniform load does that. That's the deflected shape. So I tell you what, let me ask the question differently. Of the 5 cases in the top row, which one has the greatest maximum positive moment? Ignore my question and think which one deflects the most. That's the answer. I think this one, 12 kips in the middle, causes a lot more deflection than 12 kips spread over the span. So please, whenever asked about bending moment, switch it around and think deflection. So this guy has a bending moment of 72 kip foot. It caused a lot more than 36 kip foot. Its deflection clearly is going to be a lot more. So the more the positive moment, the more the deflection. So 12 kips is the greatest. 2 6s is less deflection. 3 4s is less deflection. A uniform load is the least deflection. Okay, so that tells me about the moment diagram. Ignore it and think deflection. As architects, we understand deflection a lot better. Very good. So that's the moment diagrams for these things. And the deflected shapes. That's really what is most important. This one has the most moment. It'll deflect the most. All the others are supposed to be less, if I've drawn this to scale properly. Okay. I don't want to get into cantilevers, but I would like to say that all of these diagrams were positive. The moment diagram is positive because no matter how you load it, the top is in compression, the bottom is in tension. This is called a positive moment. And that's why this diagram was positive. This one was positive. This one was positive. This one was positive. And this one was positive. Whenever you have a simply supported beam, the moment diagram will be positive. I don't care how it's loaded. It could be loaded like that. As long as the supports are at the ends, then the deflected shape looks like that, and the compression is on the top and the tension is on the bottom. Now, when it comes to cantilevers, I don't care how it's loaded, it's going to do that. No matter how it's loaded, it's going to do that, which means the tension is on the top in every case, and the compression is on the bottom in every case. So I am concluding that this moment diagram will be negative. No matter what happens in a cantilever, your moment diagram is going to be negative. It's not going to be positive ever. Positive is for simply supported. So cantilevers will have negative moment diagrams. If you have a concentrated load, your shear diagram, I don't want to get into cantilevers. It's simple, but there's no load here. There's nothing changing. Versus the uniform load, it's probably going to do something like that. If whenever you have a uniform load, you have a slope in the shear diagram, and you have a curve in the moment diagram. I'm not interested. I'm just interested in emphasizing that in a cantilever, all your moment diagram will be negative. In a simple span, all your moment diagrams will be positive. In an overhang, it's important to understand that in an overhang, wherever you have an overhang, your moment diagram is going to be negative, but between the supports, it's going to be positive. I don't want the numbers. I just want the qualitative. It's going to be negative here. It's going to be positive here. So that's it. So that was a quick run through. Let's try to answer these questions. These are from past AREs, many, many moons ago, but the questions are good and they make good sense. Which of these two situations, A and B, will have the greatest maximum shear? Loading A or loading B? Loading A is 2 simply supported beams. Let's say, just put some numbers just for curiosity. Let's say this is 24 feet and 24 feet. And let's say this 24 feet and 24 feet. Same span and same load. For the same span and same load, which will have the greatest maximum shear, A or B? What did we just learn? The maximum shear is at the support. The maximum shear is equal to the reaction. So let's put down some numbers. If this is 12 kips, just like what we were doing, we don't need to put numbers. It's just maybe easier. So this is 6 and 6 and 6 and half of 12. And how much is the maximum shear? It's equal to the reaction, 6 kips. I'm not going to draw diagrams. The maximum shear is equal to the reaction. Very good. How about the second one? I don't know how to solve the second one. It's an indeterminate structure. Call your engineer, let them fire up the computer. But for us, I know one thing. The guy in the middle is doing double duty. It's carrying from left and right. So qualitatively, I think that this guy is bigger than everybody else. So the answer to this first one is which will have the greatest? B, middle support. Because it's carrying from left and right. So that's it. Question B, which will have the greatest maximum positive moment? A or B? I don't understand this. They're asking me which deflects more. That's what they're asking me. So let me look at the deflected shapes. Whenever they ask you about moment, think deflection. So I'm going to go here and I'm going to start looking at these guys. And I'm going to go, okay, pull out your brown. You deflect this much. You deflect this much. You don't deflect this much. That's not true because you do that. That's a continuous beam. So I think this deflection is greater than this one. So my answer to this one is the deflection of A is greater than the deflection of B, implies the moment of A caused the deflection is greater than the moment of B. That's my answer to this one. A deflects more. Okay, which will have a greatest maximum negative moment? Compression on the top, tension on the bottom. That means you are a positive moment. And so is your neighbor. We have two positive moments on the left for simply supported. You remember the diagram looks like that. It's a mirror of the deflected shape. For this one, I'm looking at it and I'm going compression on the top, tension on the bottom. Oh, but it flipped. There must have been a point of inflection and a point of inflection. And this is a positive moment. This is a positive moment. But this one here is a negative moment. The tension went to the top. That's a negative moment. Therefore, A is all positive. B has a negative moment above middle support. Does that make sense? So B is the answer to this one. It has negative moment. A does not have negative moment. Okay. Where's the maximum shear for this loading? We just did this. It's somewhere. Right? It's the reaction. I don't know what the shear diagram looks like. I'm not interested. I am interested. It looks like this. You know what it looks like. Although it's complicated, but the maximum shear is at the support. It's equal to the reaction. And the moment diagram, oh my God, this is difficult. This is negative. This is negative. This is negative. This is negative. It does something funny. Zero shear, zero shear, zero shear, zero shear. It's going to do something funky. It doesn't matter. The concepts are the same. Let me go here to this one. Loading A is 12 kips in the middle. Loading B is 12 kips in the middle, but both ends are restrained. And C is a uniform load of 12 kips. And D is a uniform load of 12 kips, both ends restrained. Everybody has a 24-foot span for the same span and the same load. I didn't say that. I'm sorry. That's what is meant. For the same load and same span. Which will have the greatest maximum shear? A, B, C, or D? So we need to just get it in our minds that the maximum shear is at the support, and the maximum shear is equal to the reaction. And the 12 kips is going 6 and 6. And the 12 kip uniform is going 6 and half of 12. And this 12 kip, I know nothing about restrained beams. They're very complicated, but I know that the 12 kip is going to 2 locations. You will take 6, you will take 6. There's moment and there's all kinds of other engineering stuff. Just ignore it. The 12 kip went to 2 supports. And the same here. And so all maximum shears are 6 kips. Are we good on that one? It's half of 12. Okay. Question B. Which will have the greatest maximum positive moment? A, B, C, or D? Again, greatest maximum positive moment, turn it off and start thinking deflection. I think I deflect like that. That's A. I think C deflects less. Maybe that much. Who deflects more, C or D? If, let's do this, copy, paste. If C does that, precision eraser, okay. If that's what C does, I think D stays put here, It's a rigid connection, and it does that. I butchered this one. Okay. So it does that. So it's going to remain 90 degrees, and then it's going to deflect a little bit in the middle. Versus this one, I think, copy, paste. If that's the deflected shape for the simply supported one, then I think what happens here is it'll stay put for a while because it's a rigid connection. And it'll go down a little bit. So which one deflects the most? I think this condition A, because the supports allow rotation. And a 12 kip concentrated causes more deflection than a 12 kip uniform. So which one will have the greatest maximum positive moment? We need to erase a little bit. Stroke eraser, okay. I think what's going on here is deflection for A is the greatest, followed by deflection for C, the 2 simply supported. I think the deflection for B is greater than the deflection for D. Okay, always think deflection and then transition. Must be the moment of A is greater than the moment of C, greater than the moment of B, and greater than the moment of D. So that answers this one. Which will have the greatest maximum positive moment? Must be A. Okay, which will have the greatest, next question. Sorry, it's kind of messy. Let's get this out of here. Sorry. Okay, let's put it over here. This one was question B. Which will have the greatest maximum negative moment? We should recognize that the simple span does not have a negative moment. The moment diagram is going to be positive. Whether it looks like this or like this, it is positive. So it must be B or D. I think excuse me, I think 12 kip in the middle is going to cause a lot more moment than 12 kip spread. So I think that the deflection or the moment, negative moment for B is greater than the negative moment for D. I think that answers the questions. And I have a key. It's in there somewhere. So those are the answers. I'm way over time, but I did reach what I would like at least. Questions?
Hey, David, this is great so far. All right, guys.
Sorry.
No, this is wonderful. And everyone has been saying, please do not apologize. That has been the message in the chat, as everyone is very grateful. So you guys, we're going to give you one last thing to be grateful for. All right, first person to put their hands up, we will take one question tonight.
One only?
One question for David, guys. Who wants to ask it? All right, we've got a taker. Give me one moment. All right, I've just asked somebody to unmute. All right, you're live on the air with David.
Hello, can you hear me?
Yes.
Oh, thank you so much for your lecture. This is absolutely, I speak for everyone. I think you're very informative and very engaging.
Thank you.
Yes, my question is, I think, probably very simple. It's about your last answer. You talk about deflection and moments, and
yes.
You're talking about fixed beams or anchored beams.
Yes.
So when I think about deflection in an anchored beam, maybe it's my lack of imagination. I don't imagine the beams deflecting upwards because they're anchored. I still imagine them going out straight, perfectly horizontal, and then deflecting at some point. Okay. So when you say a negative moment, I think of your analogy, which is, deflection. I think of upward deflection. So I'm confused about that.
How about we do this?
Yeah.
There is a beam, you load it.
Yeah.
If it's simply supported, it rotates here.
Yes.
The top went in compression, the bottom went into tension, and that's a positive moment. And there is a deflection of that much, correct? It went down.
Yes.
Very good. Now, if I have a simply supported beam like this one, it's simply supported, and I do that, it rotates here, the top goes in compression, bottom goes into tension. But if both ends are fixed, please notice the difference in these two models. I've reduced the laser cutter. There's very little area left here. That's a pin connection. This one is more monolithic. So how does this one deflect? Look at it. It stays rigid. It stays straight here. And then it deflects just very little. This one deflects a lot more. Does that make sense? So
yes.
There you go. That's the deflected shape when you have both ends fixed versus when you have both ends pinned.
Yes.
I hope that helps.
So I guess the question was which has the least positive moment. Rather, because when you said negative moment, I just imagined the beam going upwards, like it was loaded from below.
No. I see what you're saying. No. What this is saying is this remains square. The moment here is negative because the top is in tension, the bottom is in compression.
Tension, compression.
Yeah. It's the moment. It's not the deflection. Over here, the moment is positive because compression on the top, tension on the bottom. It's reversing here, which is tension on the top, compression on the bottom.
Got it. So that makes perfect sense.
Excellent.
Just one addition to that. I see when you're deflecting it, the shape is curved, but your diagram showed on a point load that it was a straight line down. Was I just misreading your diagram?
No, you were not. Since I have this on, if you imagine a cable and you do it in the middle, you get a point. That's the moment diagram for a concentrated load versus for two concentrated loads. This is for a uniform load. Does that make sense? It's a parabola.
How about if it's fixed ends or anchored ends?
If its ends are anchored, very good question, then that becomes straight. That becomes straight. And it deflects a little bit less in the middle.
Okay, got it. Thank you so much. I had 3 questions there. That's unfair. Thank you so much.
No, it's fine. I have toys to show all of this. Maybe that's the next lecture.
Thank you so much.
Please. AP, can we take another one or we're good?
Oh, we can take one more. We got one more hand up. I believe it's
Okay.
Liam. Give me one moment. I'm going to ask you to unmute, Liam. I saw you put your question in the chat, but now you can give it a voice. You there, Liam? Oh, did we lose you? All right, well, I'm going to read his question. How's that? So the question is, can you talk about compression zone tension? Nope. Okay, let me restart. Can you talk about compression zone, tension zone in a simply supported truss? I have seen one before, for example, which strut is in tension and which is in compression. So just a review of the tension compression sides, it looks like.
Leave me alone. I got toys.
Oh, we love this. Look at this. He's got a whole truss for you.
In a truss, just like in a beam. Why is this not focused? Here we go. Yeah. Come on. Okay, there we go. The top is in, if it's simply supported, the top is in compression, the bottom is in tension. So when you load it, the top goes into compression, the bottom stretches, just like a beam. Now, the orientation of the webbing is a little bit different. So in this case, it's like a cable and another cable and a third cable versus an arch, another arch, a third arch. By the way, white is compression and rubber band red is tension. So when I push down on this truss, what happens to this thing? It got longer, it's in tension. Versus the compression version, when I push down on it, the load is going to go down and stretch the bottom. But when it does that, it's like an arch taking this load and delivering it to the bottom cord and stretching the bottom cord. This is a whole another lecture. We're not going to get into this, but I can do trusses. There was 4 people on the poll that we did last week that wanted trusses. There was 6 who wanted earthquakes. So Michael and the Amber team have been very nice and generous, and we'll do different sessions. I hope I answered you on the truss question.
Looks like, yep, he says thanks. All right, thanks, Liam, for your question. All right, well, thank you so much, David, for joining us. This has been wonderful. Everyone is already eagerly awaiting your return. So next week, we're back to regularly scheduled programming, but we will absolutely let everyone know when David is back with us. So thank you so much for your time.
Thank you. I appreciate it. Thank you all, and good luck with the ARE.
All right, thanks, everybody. Good night and get licensed.
Yes. Bye-bye.